Hey guys, so this is part 2. Here we're going to talk about screws. First, let's start with the screw function. We have two main functions of the screws. If it's used alone, it could be positional screw, meaning that it just holds the two pieces of bone together, or could be a lag screw, which means that it is responsible for compression across the fracture site. If it's used with a plate, its main function is to hold the plate to the bone. Now, an important principle is 1 point of fixation equal to no fixation. So if I have an oblique fracture like what we see here, if we use only one screw, that would not be enough for two reasons. First, compression. The compression occurs only around a small distance around that screw that we have utilized. The other thing is the torque. That screw is not capable of resisting rotation around the screw. So it's not enough definitely for fixation. If we use two screws, then the second screw will give me extra compression and will also prevent rotation. But in addition to that, the leverage of compression actually, as we can see in the lower picture here, starts from the very first point of compression created by screw number 1 and goes to the very last point of compression created by screw number 2. So the bigger the distance between the two screws, the larger the leverage of compression that you can create by both screws. Now we have an ankle fracture, and this ankle fracture is a distal fibular fracture that was fixated with one screw only. So what's wrong in this picture? There are multiple problems that we can see here. First, we utilize only one screw, which is definitely not enough. Number two, this screw is probably not the correct type of screw, as we will talk about. So we have utilized here a cancel screw and instead of cortical screw. There's a cortical bone in this area, so we should have utilized a cortical screw. At the same time, this is a partially threaded screw, and a partially threaded screw, by definition, does not purchase or does not engage or does not fixate the neocortex. It only fixates the forecortex or engages the forecortex. And as you could see here in this image, the forecortex actually is not being engaged by a screw. At the same time, this screw was a cannulated screw, which means that it's much weaker than a solid screw for this in this case. And since this case was performed percutaneously, there is a chance that there is an interposing periosteum and soft tissue at the fracture site, which of course will prevent the bone from bridging and healing together. So again, one screw fixation is equal to no fixation. There's inadequate reduction and inability for the screw to resist rotational forces. So the screw elements are the following. We have the head of the screw. In the head screw, we have the recess for the screwdriver. The recess could have different shapes, could be cross, could be hexagon, could be a star. Most commonly, the star is associated with locking screws. The part of the screw that it touches the bone is called the land. Then we have the core of the screw, and we have the outer diameter of the screw. The outer diameter of the screw starts from the beginning of the threads to the end of the threads. The core of the screw is only the central part of the screw. And we also have the pitch, which is the distance between two threads. So we have different types of screw here. This part of the screw that does not have threads called the shank, also called the shaft of the screw. The area between the threaded and the non-threaded portion of the screw is called the run out of the screw, and this screw run out is actually the weakest point of the screw. As you can see here, we have different pitches for cancellous and cortical screw. They are deeper and longer in the cancellous screw, and we have smaller and shallower threads in the cortical screws. Now, the core diameter or the thread diameter, which one is used for screw size. So when I say we need to have a 4/0 screw, is that the core diameter of the screw or is it the thread diameter of the screw? Well, 4/0 is the larger diameter screw, meaning that it's the distance between the beginning and the end of the threads is 4 millimeter. As you can see here, this is my thread diameter, which is the same on both screws. This is my cortical screw, this is my cancel screw. On the other side here, we have the core diameter that is smaller in the cancel screw because we have deeper threads, and it is much bigger in the cortical screw because we have shallower threads. So screw heads. We could have large screw heads, small screw heads, or we could have headless screws. What's the difference? Where large screw heads are easy to find if you are trying to remove the screw, so it's much easier removal of hardware procedure. The smaller heads are less likely to irritate surrounding soft tissue versus large heads which are more likely to irritate soft tissue. Headless screws have minimal or no chance of irritating soft tissue. They have also minimal or no chance of causing stress risers at the bone metal interface, as we will cover this in the countersink lecture. And the threads also of the headless screws do engage the near cortex because headless screws have threads at the beginning of the screw and at the end of the screw, and that's why they engage both cortices, the near and the far cortex. What is the screw pitch? Well, the screw pitch is the distance between two screw threads. What does that mean? Well, screw pitch actually determines the distance that the screw will travel with the full rotation. So fine pitches we have in the cortical screw, that is 1.25 millimeter, and we have coarse pitches in the cancel screw, which is 1.75 millimeter. So if I make a full circle on a cortical screw, the screw will translate or will travel through the bone a 1.25 millimeter. If I make one rotation with a screwdriver on a cancel screw, that cancel screw will travel a 1.75 millimeter. However, it's to be noted that some companies like Stryker have started making screws that are hybrid. They're between cortical and cancellous bones in properties, and you could use them in both cortical and cancellous bones at the same time. Now, the core diameter, the resistance of shearing and bending forces. So core diameter is directly related to the screw's ability to resist shearing and bending forces. So the bigger the core diameter, the higher the screw's ability to resist bending and shearing forces. However, when you have a larger core diameter, this means that you will have more bone that will be removed from the area of screw insertion because you have larger screw diameter. Larger core diameter also will mean that you have shallower threads, which means that you'll get less purchase into the bone. Larger diameter of the core means you have a stronger screw. So a cancellous screw that is 4/0 is much weaker than a cortical screw that is 4/0 because cortical screw that's 4/0 has a larger core diameter than a cancellous screw that's 4/0. Again, remember that the diameter of the screw threads determines the screw size. Now, screw threads and purchase strength and pull-out strength. So the deeper threads means that there is more surface area of the screw threads that will contact the bone. This means that you have a better purchase or a better contact surface between the threads and the bone, and you will have larger pull-out strength this way. How do screws fail? We have either axial pull-out forces, bending forces, or both. These are the modes of failure of the screw, which means that the screw is incapable of doing its job. So pull-out strength is well resisted by the screw. The bending forces are the ones that are not resisted well by screws. The axial pull-out forces depend on the screw thread's depth or screw purchase, meaning that the deeper the screw threads, the better the purchase you have, the more resistance to axial pull-out forces you'll get. Make sure that you do not force screws into the bone without drilling if the screw is not self-drilling, because when you force a screw into the bone without drilling, you're actually breaking some of the threads, and this way you will have less ability to resist axial pull-out forces. When it comes to bending forces, these ones depend again on the core diameter. It's important to know that 30% increase in the core diameter gives you 3 folds increase in the resistance to bending. What does that mean? Well, if you go from a 3/0 screw to a 4/0 screw, you're actually increasing the force of the screw to resist bending by 3 times. So whenever you can use a larger screw, use a larger screw. But at the same time, you need to remember that using a larger screw means that you will lose more bone at the path of the screw. In addition to that, cannulated screws have a tunnel within the screw for the guide wire. What does that mean? Well, this means that you have a space inside the screw that is no longer considered to be part of the core. It's empty, it's hollow inside. So cannulated screws are much weaker than non-cannulated screws or solid screws, because if you have a, let's say, a 4/0 cannulated screw, the guide wire is a 4/5K wire that is 1.1 millimeter in diameter, which means that you will have to subtract a 1.1 millimeter from a 4 millimeter. So let's say about 3 millimeters are left for the core diameter. What does that mean? It means that a 4/0 cannulator screw has the same strength like a 3/0 solid or non-cannulator screw. You should not tighten the screw too much. The optimal torque is not equal to the maximum possible torque. Okay? So if you tighten the screw too much, you will cause thread stripping, and this way you weaken the screw more. At the same time, if you are tightening the screw more than a 2 finger tightness on a locking plate, that locking screw could actually becomes part of the plate. This is called cold welding. It's meaning that two metals come together, fuse together without heat. And if you're trying to remove that screw, it becomes very difficult, almost impossible, because now the screw and the plate has become only one part, one unit. It's advisable to use the torque limiting attachment if possible, because the torque limiting attachment will give you a tightness that's 2/3 of the strength or the ductility of the screw, and this is the optimal torque that you need for the screw. The screw position, well, the screw position could be either perpendicular to the bone or perpendicular to the fracture site or in between. The best possible position, if you're using only one screw across the fracture site and no place at all, is that you utilize a screw that is halfway between perpendicular to the bone and perpendicular to the fracture site. And we'll explain this in details in the next few slides. So why to insert screw perpendicular to the fracture? So let's say we have a fracture and this line here is my fracture site. If I insert the screw perpendicular to the fracture and tighten the screw, the bone will move back to its correct position. But if I have my fracture, I put my screw not perpendicular to the fracture site, I tighten the screw, as you could see, the bone will be shifted from its normal position. Now, why do we need to insert the screw perpendicular to the bone surface? Well, this is my fracture again. If I insert the screw perpendicular to the bone surface, we'll have the fracture back or we have the two bone segments back together. But if I do not, as you can see, there will be what's called telescoping, meaning that there will be shortening of the bone. The two bone fragments will move on each other. However, if we have a plate, the situation now is different, because the plate, this is my plate, this is my screw, that screw is perpendicular to the bone. There's no fracture at this area. That screw and plate, both of them, will prevent the telescoping. In this case, I could make a screw that is perpendicular to the fracture site for maximal compression. However, again, if I'm using only screws across the fracture site, it's a good idea to place your screw in between, perpendicular to the bone and perpendicular to the fracture site, in order for you to get the maximum benefit of both. Now we'll go to part 3. Thank you.